Earlier we have been considering inverters or inverting amplifiers with resistive load, and then in the last class we saw how those resistors could be replaced in the case of BJTs by current sources. Okay. Now, today we concentrate to a certain extent on such MOS circuits which do not use resistors as loads at all. That is why they have become famous in VLSI design. The MOS technology is the simplest technology compared to the BJT technology. Number of steps for the process, okay, of fabrication, they are minimal. Okay. That increases reliability of such circuits enormously. Now, in such MOS circuits, the density of packaging can be increased considerably if we just do not have any resistors at all. The resistors are replaced by MOSFETs connected suitably. Now, such inverters form the basis of logic circuits inverters. So, we have the logic family emanating from that. An inverter which uses only N MOSFET, okay, is called NMOS logic family. Okay. Same thing can be done with the help of only PMOS, then it is called PMOS logic family. And you can also obtain inverters using complementary MOSFETs, that is both N and PMOS. This is called CMOS, okay, logic family. So, these are the three important logic families which exist in, okay, your VLSI design for using MOS alone. Now, obviously, we should understand the functioning of this. Even in analog circuitry, analog integrated circuits, the same inverters can be used as amplifiers. Okay. I have told you inverter is synonymous to amplifier anyway. High gain amplifier can be used as an inverter. So, this can also be used in the active region as an amplifier. So, these blocks are also used in NMOS op amps or PMOS op amps or CMOS op amps. Okay. So, these are the basic building blocks which are used in also analog ICs. So, let us understand these also. Now, consider first this circuit. This is nothing but the common source amplifier with a load resistance here. Source is common to input and output. So, the same common source amplifier which we have discussed earlier with resistive load now is being discussed with resistor replaced by a MOSFET. How is this MOSFET connected? We do not want any resistors at all coming into picture. So, and also we do not want to use further voltage sources other than VDD, in which case this gate is a terminal, okay, which should be connected to something. Okay. The only thing that if you connect it to source, it will not conduct at all, because it requires a gate to source voltage higher than the threshold voltage. Whereas, if you connect the gate to the drain, that means VDG is made equal to 0. That means VDS, this is VDS, is always equal to VGS. So, this is an important situation here. VDS is always equal to VGS, right. We will call this T2, this as T1. Now, this is VDS2, this is VGS2, okay, and VDG2 equal to 0. Therefore, VDS2 has been made equal to VGS2 in this case. So, what is the state of affairs as far as the T2 is concerned? T2 therefore is always in current saturation region. Why? Current saturation region, a transistor is going to be as long as VDS is greater than or equal to VGS minus VT. Here VDS is always equal to VGS, and therefore, we have this transistor always remaining in current saturation region. So, this is what is called as enhancement type of load. Okay. For this MOSFET, this is an enhancement type of load. In such a situation, let us try to plot V naught as a function of Vi. This is what we had done in almost all the inverters earlier also. Now, in this situation, what happens? When Vi is less than Vt, let us say this is Vt, this transistor is off. So, when Vi is less than Vt, T1 is off. Right. So, V naught is going to be equal to, now that is important, V naught is going to be equal to VDD minus VGS2. VGS2 should be hovering around even when current is 0 at Vt, that is when VGS2 is equal to Vt, current is 0. So, that is a valid operating point. Therefore, VGS2 drop of Vt is always going to be there, whether it is 0 current or higher current, it will be higher, okay, correspondingly. So, this voltage V naught, which is VDD minus VGS2, okay, is going to be, this is V naught is equal to VDD minus VGS2 always. When the current is 0, VGS2 is equal to Vt, and therefore, it is starting at VDD minus Vt. This is an important aspect of enhancement type of load. The high level in any inverter should be normally equal to VDD itself, right, but it is not so in the case of this kind of inverter. This is a disadvantage, okay. Because we want simplicity in its structure, we have to live with this kind of disadvantage, okay. So, it is VDD minus Vt up to Vt, this is going to be the output potential. Thereafter, let us see what happens. Thereafter, this T2 is always going to remain in current saturation, that we know. As far as this transistor is concerned, in what region is it likely to be? This potential is very nearly equal to VDD. So, VDS is obviously much greater than, okay, this VGS minus Vt, hopefully. Therefore, this T1 to begin with is in the current saturation region. So, both these transistors, when we enter conduction, are in the current saturation region, which means, okay, the current in this, how much is that? Current in this is going to be ID S1 is going to be K, okay. The K of the this thing, this MOSFET is assumed to be the same as K of this MOSFET, because these are identical, okay. So, K into VGS 1 minus Vt whole square. Okay. What is VGS 1? This is VGS 1, which is Vi itself. So, this is K into Vi minus Vt whole square. This current is same as IDS2. So, this is same as IDS2, which is going to be K times how much? VGS2 minus Vt whole square, because that also in the current saturation region. So, now assuming that this K is governed by its W by L ratio, that is the only thing that can be different. Vt's are going to be the same because they are the same type of MOSFETs. Vt's are going to be the same. K's can be made equal if W by L ratios are made equal. Right? Now, we have to see whether we have to make W by L ratio equal in order to design a worthwhile inverter, or W by L should be same. Okay. Now, therefore, we will call this as K1 and we will call this as K2. K1 and K2 will be directly dependent upon W1 by L1 and W2 by L2. Okay. So, these are the equations to be satisfied, and VGS2 is therefore equal to how much? VGS2 here is nothing but VDD minus V naught. So, from this important relationship we get the transfer characteristic of the inverter. How is it going to be? It is going to be perfectly linear, right? It is going to be linear. Why? This square, this is square and this is square. So, we get, you can equate these two, you get VDD minus V naught minus Vt equals, okay, root of K1 by K2, root of K1 by K2 into Vi minus Vt. Is this clear? Or V naught therefore is equal to, you just take V naught onto that side, VDD minus Vt, VDD minus Vt, V naught is taken that side, minus root of K1 by K2 Vi. So, if you plot this, this is the slope negative, indicating that it is inverting, okay? And the magnitude of slope depends upon what? Root of K1 by K2. For a good inverter, we have mentioned that this slope is nothing but, what is it? The gain of the amplifier in the active region, right? The slope is nothing but the gain of the amplifier in the active region. This should be both in the digital inverter as well as amplifier very high. That means K1 should be much greater than K2, okay? Or W by L ratio of transistor 1, okay, should be much greater than W by L ratio of transistor 2. Is this clear or not? So, this is the design aspect. So, if you make them identical, then it will be having unity gain, which is, okay, not good either for amplification or for inverter application in the case of a digital circuit. So, this is always what is done. Now, let us see how it progresses further, that this voltage will keep on decreasing as you progress. Okay. This voltage, output voltage, will keep on decreasing. VGS2 will keep on increasing for higher and higher currents. Okay. So, this voltage will keep on decreasing. A time will reach when this voltage, which is the VDS of this transistor, becomes equal to VGS, that is Vi, minus Vt. That is when this transistor enters the triode region. What is that region? Let us again put VDS, that is V naught, when that becomes equal to VGS 1, which is Vi minus Vt, the transistor T1 enters what? Triode region. So, this is nothing but a line. Let us say this is a line which is starting at V naught equal to 0, Vi is equal to Vt. So, with a slope of 1. This is V naught equal to Vi minus Vt. This is another line whose equation is already known. This equation is the equation of this line, this equation is the equation of this line, and intercept is the point where it is entering the triode region, right. That you can evaluate, because you have two equations and two unknowns. So, you can find out V naught and Vi at which this happens. So, that I am going to leave it as an exercise for you. Solve these two equations and obtain V naught and Vi at this point, the transition point. Thereafter, this equation is going to change, right, because it has entered the triode region. IDS1 is no longer K1 into VGS1 minus Vt whole square. It is equal to what? 2 K1 into VGS1 minus Vt into VDS, which is V naught, minus V naught squared by 2, VDS squared by 2. So, this is the equation that is going to be valid, and VGS1 is equal to Vi. So, now you will see IDS2 is going to remain the same, only IDS1 is going to change, right. Again IDS1 is equal to IDS2. Now, this is no longer linear, this is a non-linear, because you have square, linear and square here. So, this is a non-linear relationship, and if you solve for V naught using these two equations, equate these two, then solve for V naught. It is a quadratic equation in V naught. Solve for V naught and obtain that. That again is going to be left as an exercise for you. These two equations you must take, equate them and solve for V naught. So, both T1 and T2 are in current saturation region. Here T1 is off, and T2 always in current saturation, and here T1 is in the triode region and T2 in current saturation region. So, you can use this as an amplifier, and that is beautiful, because you are using a nonlinear load and transfer characteristic becomes perfectly linear, and the gain is root of what? K1 by K2. So, if you use it as an amplifier, for example, in an NMOS operational amplifier, the gain is straight away known as root of K1 by K2. This is not small signal gain, this is large signal gain, it is linear. So, because there is a nonlinear characteristic here and there is a nonlinear characteristic here, these two nonlinearities cancel one another and you get a perfectly linear relationship here. Okay. So, therefore, it is perfectly linear here up to this point. Anyway, this region we are ignoring because the amplifier is going to saturation, right. So, this T1 is going to triode region. Okay. So, this is the operating point. In between these two can be the operating point, so that you get maximum signal swing. Okay. So, you can select appropriately. Once you know this point as well as this point, you can select appropriately the bias point here, okay, as the center point between these two, okay, half of this plus this voltage. That will give you the maximum swing. So, even if this is made out of PMOS, almost similar analysis is valid. The characteristic will be exactly identical. Only all the things will happen for negative voltage, that is all. Okay? That is the only difference. But the entire analysis, the structure, everything remains the same. Okay. Another alternative is to go for what is called as depletion load. This requires a diffused, okay, channel here. This we know. In order to make a depletion MOSFET, we have to diffuse the channel, and therefore channel exists. So, it is conducting. Okay. Even when VGS is equal to 0, it is conducting. Now, this is a nice thing. VGS can be made equal to 0. That was not possible here, right. So, we can make VGS equal to 0. If VGS is 0, okay, it will have a current of ID SS through it. If the voltage across this exceeds the pinch off, but below pinch off, okay, it is going to act like a almost like a resistor, right. So, this is the advantage, and therefore, the voltage drop when it is 0, that current is 0. Okay. When the current is 0, the voltage drop is 0. That means, the voltage here can start now from VDD itself. So, between this and this, you have this disadvantage here, right. So, it will straight away start with VDD. So, its transfer characteristic, now if you plot, it is going to start at VDD. Then at that point of time, this transistor is going to be in the triode region, and this transistor is going to be in the current saturation region. Now, things are slightly different from this. This is going to be in the triode region, and this is going to be in the what? Current saturation region. So, you can once again start off this whole thing for the second circuit, where depletion type of load is there. Until Vi equal to Vt is reached, okay, this transistor T1 is going to be off. But the voltage is going to start now from VDD. Why? The T2 is in the triode region for VGS equal to 0. So, T2 is in the triode region, T1 is in the current saturation region. Up to Vt, this will be the case. Thereafter, what happens? T2 will continue to be in the triode region. T1 has now come out of off state, right. It is in the current saturation region. Actually, this is T2 in the triode region is going to be here, sorry, T2 in the triode region in both these places. T1 here is off and T1 has entered current saturation region. That means IDS1 is going to be K times Vi minus Vt whole square, that is valid for T1, like it happened here. But for T2 is going to be, okay, this is going to be in the what? Triode region. So, its current is, I mean, you cannot write it as 2K strictly speaking, because this characteristic is now going to be IDS equal to, okay, IDSS, right, in the current saturation region 1 minus, okay, VGS by Vp whole square. Okay. This is the equation for the current saturation region of depletion type of MOSFET. Is this clear? For the other region, that is for the triode region, IDS is going to be twice IDSS. It is going to be similar, right, mathematically it is similar, into 1 minus VGS by Vp into, now VDS and Vp are opposite signs. So, we put for the magnitude of current this, because we have known the current direction. So, right, magnitude of current only we are interested in, half of VDS by Vp. Now, this current is going to be equal to this current IDS2. VGS in this case is 0 at all times. So, this is 0. Okay. This into VDS minus Vp, that is all, 1 into VDS minus Vp, and VDS for this VDS, okay, is going to be VDD minus V naught. This also is going to be VDD minus V naught square. So, this is the equation that one has to satisfy. Once again, you see that this is highly nonlinear. Okay. You have square here, but no square here. So, this is nonlinear. So, this is going to follow some kind of relationship like this, right, and then this voltage is keeping on decreasing. Now, T2 can enter, okay, the current saturation region, T1 remaining still in current saturation region. T2 can enter current saturation region, T1 still remaining in current saturation region. Okay. So, that is the point where obviously the current in this is going to remain constant at IDSS thereafter, right. So, this is going to remain now constant at IDSS. Okay. This current is going to remain constant at IDSS, and this current is going to be equal to IDS1 equal to K times Vi minus Vt squared is going to be satisfied. Okay. So, what is going to be the gain is going to be a current source, as long as this is remaining constant at IDSS, this is going to act like a current source. Okay. The gain is going to be infinity, right, strictly speaking. What is the slope therefore? Okay. This is going to be almost vertical here. Right. This is going to be the case as long as this particular thing is going to remain in the current saturation region. At point will reach when this transistor will enter the triode region. Okay. This is going to enter the triode region. So, this is going to go on until the transistor enters the triode region. Once again we can draw the same line, that line remains the same, that is corresponding to V naught equal to Vi minus Vt. And thereafter the output voltage is going to remain, this is IDSS, depends upon, this is going to act like some resistor here, right. So, it depends upon the potential that this develops here, right. So, output voltage is going to depend upon this, and again it is going to be non-linear. So, this is the advantage of this scheme, when the both this and this are in the triode region, we have this acting as a high gain amplifier. So, the slope is going to be infinity, and the transition is going to take place like this here. Unlike this situation where the slope depends upon the K1 by K2 ratio, here we have the slope becoming equal to infinity. We had seen that this region, the transition region, where both T1 and T2 of this inverter remain in the current saturation region, is a very important region, because that is the region, active region, in which gain is very high, infinity. Now, in actual practice obviously gain is not infinity, because this, when it enters current saturation region as well as this entering current saturation region, there will be this RDS of each of these FETs, RDS1 and RDS2 coming into picture. So, RDS1 parallel RDS2 into GM of the FET is the actual gain. Under this case, when we have assumed that these are ideal current sources and sinks, the gain looks to be infinity. So, this is that region. Further, the T2 triode has entered into current saturation region here, where both T1 and T2 are in current saturation. So, this transition region, how do we obtain? That is the region where VGS is 0. When VGS is 0 for the transistor T2, the transistor enters the triode region when VDS becomes equal to VP. VDS in this case is VDD minus V naught, becomes equal to magnitude of Vp. Right. So, this is the point, that is you can now find out from this the value of V naught at which the transistor T2 is entering the triode region. That is when this VDS becomes same as Vp. VDS being equal to VDD minus V naught becomes equal to magnitude of Vp. Is that clear? Now, that is something that you have to remember. That is this point. This point we have already seen is the point corresponding to V naught equal to Vi minus Vt, where T1 goes from current saturation to triode region. Thereafter, of course, we have this. This completes the characteristic of the inverter. I would like you to evaluate the transfer characteristic for this portion, where the entire amplifier is in saturation. Equating the for T1 current in the triode region to the T2 current in the saturation, that is of course IDSS. Now, we go to an important basic building block, that is the CMOS inverter, as shown here. So, unlike the other inverters which used the same type of enhancement MOSFET, either N or P, here we are using NMOS and PMOS in combination, the complementary MOSFET. This is the most important basic building block for VLSI design. Also, it is used as an inverter in analog circuitry. Let us see what it is. Here, just as we did the analysis in the case of these NMOS circuits, we can also do the analysis in an identical fashion and come up with the transfer characteristic. So, let us once again obtain the transfer characteristic for this V naught and Vi. Now, you have become almost familiar with the routine that we are going to go through. When Vi is less than Vt, T1 is off. When Vi is less than Vt, right. Therefore, T1 is off, T2, because Vi is less than Vt, no current is flowing through this. As far as T2 is concerned, this voltage is going to be extremely small, the drop across this. V naught is going to be very nearly equal to VDD. T2 is going to be in the what? Triode region. Please see, Vi is connected to, let us say, ground, 0. This is conducting. This is conducting. There is considerable amount of voltage applied to this. This is conducting. It is only that this is not conducting, but this is in the triode region. So, T1 is off, T2 is in the triode region. If Vi goes very nearly up to VDD, this can be made to go off, right. So, when Vi is 0, T2 is conducting, but T1 is forcing the current to be 0, because the currents in these two must be same. Now, as long as the Vi is less than Vt, T1 will remain off, and this is going to be at VDD. So, once again we are having the high level going almost up to VDD, no problem. Thereafter, T1 starts conducting. T1 is going to be in the current saturation region, because V naught is very nearly equal to VDD. Okay. So, T1 is in the current saturation region. But T2 still remains in the what? Triode region. So, characteristic is going to be non-linear because T2 has remained in the triode region and T1 is in the current saturation region. Okay. We can write down the equation ID S1 is equal to K1, okay, into VGS1, which is VI, minus VT1, we will call it, right, squared. This is in the current saturation region. This is equal to, okay, now we have to be careful, we will only put the magnitude of current, okay, consider it as positive, IDS2, okay, this is equal to, now this is in the what? Triode region, okay. So, 2K2, right, into, now let us see, we have to keep this positive all the time, okay. So, first you get VGS2, right. Now, VGS2 is VI, okay, minus VDD, but we will put VSG2, okay, which is positive, VD minus VI minus, okay, magnitude of VT, because this is, okay, negative. So, VT2, okay, this is negative, right. So, now this remains positive, right. Is this clear? Or else you should have put it as VGS, which is VI minus VDD minus VT2, that is all, sign being taken care of properly. Here, in order to prevent any confusion, I am putting all quantities as positive. VDD minus VI, okay, is the positive voltage, minus VT2, okay, into what? VDS, okay, again it is V0 into VDD, whereas we will put it as VDD minus V0, okay, minus VDD minus V0 whole squared by 2. Is this clear? So, there is not going to be any confusion here, otherwise, okay, you stick to the original equation with signs being properly taken care of. So, this equation will give you some kind of nonlinearity here up to a point. This will go on. The triode region T2 remains until a point is reached at which it will come into current saturation, that we have to find out. What is that point at which T2 comes out of current saturation triode region into current saturation region? Let us see. That is the point where, okay, VDS, which is, we will put it as VDD minus V0, okay, this voltage becomes equal to VDD minus V0, okay. Actually VGS, we will put it as VSG, okay, VDD minus VI minus magnitude of VT2, no problem, okay. So, this is the point at which this is entering current saturation region. What is this? You can cancel VDD, this, okay. So, this is nothing but V0 equal to VI plus magnitude of VT2, another line, okay, which is going to, if this is VT1, okay, the intercept here is going to be at VT2 when Vi is equal to 0, and it will go on like this. This line is going on like this, okay. this line is V naught equals Vi plus Vt2. This line, which was earlier itself known, V naught equals Vi minus Vt1. So, within this region both the transistors are in current saturation region. That means this equation is no longer valid. IDS1 equal to IDS2, this is equal to T1 and T2 in current saturation region, and therefore is going to be infinite gain, slope is going to be infinity. Okay. This will go on until the now lower transistor T1 goes into triode region. So, what is that IDS2? It will be K2 into Vi of that is this, which is strictly speaking how much is it? This Vi, this is actually, which is nothing but Vg S2, which I am putting as Vdd minus Vi, minus magnitude of Vt2 whole square. Okay. So, you can see that this is perfectly linear. Okay. This is going to be perfectly in the sense linear, and slope is equal to infinity, and this is the region where the amplifier is in active region. Okay. Now, you can also from this equation find out the value of Vi, at which it will remain with slope equal to infinity. So, you can find out from this equation the value of Vi. If K1 is equal to K2 and Vt1 is equal to Vt2, you can show that this will occur at exactly equal to Vdd by 2. If K1 equal to K2, Vt1 equal to Vt2, this transition will occur exactly at Vdd by 2. That is the ideal inverter characteristic, where the transition from high to low occurs exactly at Vdd by 2. Thereafter, what happens? This transistor enters the triode region. The story is exactly similar to this region. Since it is symmetric, it is exactly similar to what happens in this region. So, I would leave it to you to complete this. Ultimately, this as it reaches what value? When this reaches Vdd minus Vt, the upper transistor goes to off state, right. So, Vdd minus Vt2, right, the upper one goes to off state, and the output is going to be 0, no current, and up to Vdd. So, this is a complete characteristic of this CMOS inverter, and it is the closest to an ideal inverter. There is no other inverter which is approximating to the ideal inverter. Gain is infinity, and the transition, if they are perfectly symmetric, if K1 is equal to K2 and Vt1 in magnitude is equal to Vt2, then it is going to transit at Vdd by 2. Correspondingly, you can find out for this value of Vi what the V naughts are. You will get the, from this you will get one value of V naught, and from this you will get another value of V naught. So, I would like you to complete this and obtain all the critical points in this.